like classes where you're not meant to learn anything. You just gotta.
You are meant to learn. That's not mine.
No.
I intend for you to learn something each and every day, but you just don't. Yeah, whether you do it or not. Sometimes you're the one who's learning things.
I am.
Especially with our class. All right, guys, here we go. So 4-4 is the basics, and then 4-5 is actually, putting the multiplication rule into effect in some other situations. So I'm going to get the multiplication rule today. So 4-4 and 4-5 are both multiplication rules. So that's why we're doing them together out of that. So get the basics of it out of the day. Okay, so the basic multiplication rule is used for finding an AND event. Last week we talked about OR events, and that was the addition rule. AND events are multiplication rules, okay? So event A occurs in the first trial, event B occurs in the second trial. What we've got to decide is, are those independent events or dependent? So does the first one affect the second one? And the best example I can give you of the second one being affected by the first is if, like, we're drawing a card from a deck. If we put the card, we draw a card, we get a Queen of Hearts, we write that down and we put the card back and then reshuffle, that's independent because there's still 52 cards in the deck for the next draw, right? But if I pull that Queen of Hearts out and I say, oh, Queen of Hearts, and I lay it over here, and then I go back to the deck, what's different? Not the same number of cards. So that's a dependent. The second draw would be dependent upon the first one because I didn't replace. So if there is no replacement or without replacement, then they're dependent. If there is replacement, then it's independent. Okay, so that's a good way to think about that. That's a good example of deciding that. So very important that we adjust the probability of the second event if it is affected by the first. So we got to be careful of that. That's the main thing that we're after here, is make sure we're taking care of that if it is affected. All right. All right. Probability notation there. A and B, event A occurs in the first trial, event B occurs in the second trial. This notation here, that's B given A. Okay, that's what that stands for. Okay, it represents probability of event B occurring after A has already occurred. Okay, so B given A, that straight up and down bar, that's how you read that. Probability of B given A. So that means B happens and A has already happened. Doesn't necessarily mean that A and B were dependent upon one another. It just means that A happened first. Multiplication rule uses that notation. That's wrong. So it's the probability of event A times the probability of event B given A has already happened. Okay, that is the formal multiplication rule. So that is the same rule no matter whether they're independent or dependent events. The rule doesn't change. Okay? Independent or dependent, the rule doesn't change. With the OR problems that we did last week, if you had overlap, then you had to take that out. So there was that extra subtraction that you had to do in that. If there was overlap. If there wasn't overlap, you didn't have the subtraction. So you had to be careful of that. Here, we've got to decide before we do this, are they independent or dependent? The rule stays the same, though. It's probability of A and then times the probability of B given A has already happened. So we decide if it's independent or dependent before we even start. Okay? All right. When we're talking about this, we're finding the probability of event A occurs in one trial, and then event B occurs in the next one. We're going to multiply those probabilities together, but we have to be sure that the probability of B takes out the previous occurrence of A. Okay? If they're dependent, A is going to affect it. All right? If they're independent, A is not going to affect it. So our probabilities are a little easier to do. When they're independent events, that's much easier to do. So make sure we're taking into account B. When we're taking into account, did A affect make sure you're taking that into account. In that same line there, we've always got to consider the independent and dependent event part. That's the first question we've got to answer, and that adjusts our probabilities based on that. And our calculations are a little bit different based on that independent and dependent. We're going to get some examples of that. Okay. All right. Because it's not hard once you get to the examples. It's pretty easy stuff. Get to the hard stuff in the week. All right. Multiplication rule for several events. Probability of any sequence of independent events is simply the product of their corresponding probabilities. So if I told you to roll, a rolling die 5 times, your probability of rolling a 2 each time is 1 out of 6, right? Every time you roll, it's the same probability. So if I told you to do that 5 times, what's the probability of rolling a 2 every single time? It'd be 1 out of 6 times 1 out of 6 times 1 out of 6, 5 times. 1 over 6. So that's just independent events. It's simple to do the probabilities. You're just going to multiply those together. See? Probability of any sequence of independent events is simply the product. Multiply them together of their corresponding probabilities. Okay. All right. There we go. 2 events, A and B, are independent if the occurrence of one does not affect the other. Okay. If I'm rolling a dice, one rolling die each time, what I roll on the previous one doesn't affect the next one, right? Because it's the same cube every time out of that. Several events are they call similarly independent if the occurrence of any does not affect the probabilities of the occurrence of the others. Okay, so A and B are not independent, then they're said to be dependent events. Okay, independent events, first one does not affect the second one. Dependent one, they do. Okay, so we've got to decide that first. 2 events are dependent if the probability of the second one is changed because of the first one. It doesn't necessarily mean that one causes the other one to happen. So don't infer that that's what's happening. The probability of event A doesn't necessarily make probability of event B, doesn't make it happen. It just makes it, the probability is different. Dependent events. We can treat some dependent events as independent based on these criteria, okay? Some of the cumbersome, I like that word, cumbersome calculations can happen. They can be made more manageable by using the common practice of treating independent events as independent when there's really small samples. So if you only had 5 options out of that, and they're drawn from a very large population, but it's a really small sample, then you could treat them as independent instead of dependent if it's a really small sample from a very large population. And we'll kind of see some of that as we work through some of those problems when that can happen. And so sometimes that can happen. For the most part in here, you're probably not going to see that a ton. We'll actually do the actual calculations. Because we'll get to too large numbers. 5% guideline here. So this is one of the criteria for that. If the sample size is no more than 5% of the size of the population, treat the selections as being independent, even if they're made without replacement, so that they're technically dependent on one another. So that would be like our school number size for 7 through 12 right now is 721 students. That's what we have in the building on our rosters. So if I had a sample size that's less than 5%, what size is that sample? What's 5% of 721? Do the calculation. 36. So if I were using you guys as a sample, and I was gonna, do a probability situation, and I selected, what's the probability of picking a female, whatever I'm picking a girl first. Event A is picking a girl. You guys are my sample. What's the probability of picking a girl out of this sample? Eight out of 15. Today it is 8 out of 15. So 8 out of 15. And then, so that would be probability of event A. And then I'm going to pick a second person, and I want to know I say, okay, that person is not replaced. And I want to pick, the second event is picking a boy. The probability of that would be 7 out of 15, right? If I don't replace it, normally I would say, well, it's 7 out of 14 because I didn't replace the girl that I selected first. But because our sample size is less than 5%, then I'm going to treat them as independent. So I'm going to treat it as if I did replace that girl, because my sample size in here is less than 36. 5% of 721 is 36 point something, but 36 people. We've got less than 36 in here. So that's one of those scenarios where my sample that I'm drawing my probabilities from is less than 5% of the population for the school. So if I did those events, because of that, I can treat them as independent, even though in reality, we know that there are dependent events if I don't replace. And so that's one of those 5% rule things there. That doesn't come up a ton, but it is one of those rules that can be, come back and get you if you don't remember it. And so that 5% rule. All right, so here's just an example. This is where it starts making some sense. Okay, suppose 50 drug test results are given from people who use drugs. So you have positive test results. There's 44 positive test results, 6 negative test results. 50 of them total. If 2 of the 50 subjects are randomly selected without replacement, find the probability that the first person tested positive, the second person tested negative. And notice it says without replacement. Okay, so this is one of those where it's not a sample. It's, our population is these 50 people. Okay, what's the probability of, we're going to probability of first positive, second, and second negative. So without replacement, because that's in bold and italics there. So what's the probability of the first one being positive? How many people are positive drug tests? 44 out of 50. We could obviously reduce that fraction if we need to, but we don't have to until the end. Okay? And then without replacement means, okay, if I pick one of these, how many are left? 49. And the second one being negative, how many negative ones are there? 6. So we multiply those two together to get our probability for that and situation, those two events. So multiply those. Let's see. 22 times 6, 132. And I just help me out there for 25 times. How much? 1,225. And then give me that as a decimal. 2. 107. Why'd you go 3 places? That's the what?
The rule.
The rule.
No.
Yeah, why is it the rule?
It would have been 8.
What is it? What is it after that?
I just did
7.
So there's a 7 after that. So round that up. 0.108. 3 significant digits. Remember, probabilities, we're going to go to 3 significant digits. So this 0 here doesn't count. You go 3 digits after the decimal place there. But there's the fraction result. There's the I don't know what it is.
1 is really good.
1, what do you need, bud?
You know how they give messages to students? They walk around and give them a piece of paper and says like, "Write what's home." Like, do they only do that with that kind of stuff, or could they do like a death in the family like that?
I wouldn't know that. I wouldn't. I don't think they do that.
Just like
Dad.
Yeah,
What do you get? Actually,
I'm glad.
All right, so here's the electronic version of that. You got 44 out of 50, 6 out of 49, multiply those together, and there's our decimal 1 or 0.108. Okay, so 3 significant digits on the decimals. With that. Questions about that? So was that a dependent or independent event? Dependent, because the second one was affected by the first. All right, here's another example. 2 different people are randomly selected from those in your class. Find the indicated probabilities by assuming birthdays occur on the same day of the week with equal frequencies. So we're going to assume that that's what's happening, that the probability of a birthday on a Monday is equal to the probability of a birthday on a Friday, that you were born. So I don't know what the numbers say about that worldwide. I don't know if it exactly is that, but I would think it would be close. Part A says probability that 2 people are born on the same day of the week. Okay. So we're looking at probability of same day of the week. So A and B, same day. Well, not necessarily, because we're looking at days of the week, not peak population of the world. We're looking at probably how many days of the week are there? 7, right? Good job. 7 days of the week, we know that. Does it matter when the first one is born? No. So probability of A is going to be 7 out of 7, right? It could be any of the 7 days. And then the probability of B, it's got to match that, so it's got to be 1 out of 7. Okay? Is that an independent or dependent event? It's independent, because when Brett was born didn't affect when I was born didn't affect when Brett was born. Okay? So what are we going to do with those? Multiply them together. 7 over 7 is really 1. 1 times 1 over 7 is going to be 1 over 7. And, well, I don't want you to be yet. So 1 over 7, and let's get that at, so 7 over 7 times 1 over 7 be 1 over 7. What's that as a decimal? 3 significant digits. 0.143. Okay. So there's our probability for A part. B says the probability that 2 people are both born on a Monday. Lose some.
Molly was born on Monday.
How do you know these things, Molly? Molly's over there for a cat. How do you know these things?
Oh, because you were born on Sunday.
I was born on Sunday.
Right, and your birthday's around. That's kind of freaky one.
He's like, by the way, you were born at this time.
By the way,
You were born on Tuesday.
All right, so B part. Let's look at those. Both of them were born on a Monday. So what's the probability of being born on a Monday?
1 out of 7.
1 out of 7. So probability of A, the first person, 1 out of 7. Probability B, second person, probability of being born on a Monday. Is it affected by the first person being born on Monday? No. Still 1 out of 7. So we're multiplying those two together because they're independent events still. 1 out of 49, which is what is a decimal?
0.07.
What? 0.07 something. I didn't know something. What?
0.020. Well, no, when you go more than that, it's like 020408.
So go 3 significant digits. So it's 0.020408, and then my calculator goes 16. If we go the right number of places,
It'll go to 8.
204. That's 3 significant digits. This 0 doesn't count. Any of them after that do, though, because we had a digit that started there. So the 0 in front does.
Significant digits and not just say skip the first 0.
That's what significant digits do.
That's just a lot easier. Because it could be 2 zeros too.
Because there could be a bunch of zeros there.
God, why'd you do this?
It could be, your probabilities, could end up being like this. If you just skip the first one, then you go till you get a digit. Right.
Yeah, well.
All right, so 1 out of 49.0204. 2% probability of that happening. That 2 people selected would be born on a Monday. All right, tree diagrams. Neat way to help us out with probability is a tree diagram. A tree diagram is a possible outcome kind of situation, kind of like a tournament bracket type look to it. We start with the first event, and then we go branches off of that with the second event. Okay. Sometimes helpful in determining the number of possible outcomes in a sample space, and also helpful in finding the actual sample space. Okay, that's what a tree diagram is good there. Usually, for dealing with a lot of options, a tree diagram can get kind of big and cumbersome. So we don't want the number of possibilities to be too large. What's too large, I'm not sure. But this is what a tree diagram kind of looks like. Okay, so your first choice for a true-false question, followed by a multiple choice question. So your first option is true or false. And then the second question, you could have 5 answer choices for. So your answer document could have true, then A, B, C, D, and E. Or your answer document could have false, then A, B, C, D. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ways that your answer document could be filled out. 10 possible combinations. Well, especially with math tree. That's where it is. All right, so tree diagrams, being able to build one of those. Be able to do that, okay? Not a hard thing to do. First event, and then branches for the second event, okay? Addition rule for OR problems is addition. Probability of A, probability of B. Careful not to count the overlaps. You got to subtract away the ones that fit both situations. Make sure of that. Okay, multiplication rule is for AND problems. Okay, multiply probability of A, probability of B. Make sure you're deciding it's independent and dependent. Make sure you decide that. Because if event B is affected by that, like you don't put the card back in the deck. That's a good example of it being affected and then being dependent events. So be careful of that. All right. Here's a little flow chart. Multiplication rule, because it's an AND problem. Are they independent? Then just multiply them. Probability of A, probability of B. If they're not independent, then you got to take into account the not putting it back in the deck, the without replacement idea. So just make sure you're thinking of that. Okay. We'll kind of build larger flow charts as we go through this chapter and get more things happening. So some small pieces in there. All right, let's get to the next section. That was section 4.
That was the big one.
That was the basics. Let's do something a little more less, a little less basic here. All right. Multiplication rule involving complements and conditional probability. Okay, so this is one that gets a little bit more complicated. Complements, that's like complement, not like I like your shirt, Juan, or nice hair. You know, it's complement as in the opposite. Like, you remember in geometry, the complement of an angle was what it needed to be added to it to get 90. So it was the leftover part. So complements in stats is kind of the leftover part. Conditional probability, conditional. It's got a statement that's going to tell us some things after that. All right. Key things we're going to look at here. We're going to look at the probabilities of at least one. So it's like the probability of at least one person scoring an A on this quiz. No, I'm just kidding. It's not. You guys will be fine. Find the probability among several trials we get at least one of a specific event. Okay, at least one. We're going to look at that. Conditional probability we're going to look at is the find the probability of an event we have additional information that some other event has already occurred. So it's one of those given something's already happened. That's what the conditional probability is. All right. Probability of the at least one cases. Okay. The at least one case is one or more occurrence. Okay. It's one or more occurrence. Okay. That's what at least one means. The complement of getting at least one item of a particular type is that you get no items of that particular type. Okay, so the probability, the complement, when we're talking about complement, is no thing. Like, how many people in there are 18 already? Anybody? Just one? Okay, so the probability of at least one person being 18 in here, we're going to use the complement of that. So the complement of that would be, there's 1 out of 15. Complement of that would be 14. That's what we're going to be using to help us with this. All right, so here's how you're going to do that. Probability of at least one is easy to calculate by subtracting the result of 1 minus the probability of it not occurring. Okay. Probability of no one, okay, or none of that event happening. Okay. At least one is 1 minus the probability of that event not occurring. I'll give an example. It'll make a little more sense. The probability of at least one is 1 minus the probability of that not happening. No occurrences. Make sure that makes it much easier to find. All right, here's just an example. Tomford supplies X data DVDs. Somebody uses it anymore. In lots of 50, and they have a reported defect rate of 0.5%. So the probability of a disk being defective is 0.005. So they converted that decimal or that percent to a decimal for you. It follows that the probability of a disk being good would be 0.995. 1 minus 0.9. What's the probability of getting at least one defective disk in a lot of 50? So if we bought a spool of 50 of these DVDs, and what's the probability of at least one of them being defective? Could be all 50 of them being defective. Could be 49 of them. Could be 12 of them. But what's the probability of getting at least one that's defective? So this is how we would do that, okay? Probability of at least one defective disk in 50. We're going to take 1 minus the probability that all 50 are good, okay? For all 50 of those disks to be good, that probability is going to be the probability of it being good, 0.995, right? 50 of those occurrences would be 0.995 times itself 50 times. 50 independent events, right? So that's what this means. When you raise 0.995, to the 50th power, that's saying you've got 50 discs and you're multiplying their probability of being good times themselves 50 times. Okay? We work that number out and then we subtract it from 1. That number ends up being 0.778, so 77.8% chance of all 50 of them being good. 1 minus that, so it's a 22.2% chance of at least one of those discs being defective. Not hard calculations, you just got to remember that rule and know how to figure out the probabilities of everything being okay on problem. So not hard math at all. Math's easy. Knowing what to do and how to do it. Conditional probability. So we got the at least one idea. That 1 minus probability of none of those occurrences is the at least one idea. Conditional probability, it would be is the B given A thing happening here. All right. Conditional probability. We got a little formula here that we can go by. Probability of A and B over probability of A is the given probability. That's something we need to know. Okay. Probability of event of B occurring given that A has already occurred. That's what that means. And it can be found by dividing this product, the probabilities of events A and B both occurring by the probability of just event A. Get that formula, that's the key. The conditional probability. The biggest thing here is you're going to be practicing problems. Make sure once you figure it out, it's pretty quick and easy. Probability of A and B divided by probability of A. Both occurring. And probability of the first one. B given. Probability, conditional probability B given A can be found by assuming that event A has occurred and then calculating the probability that event B will occur. So it's the intuitive approach as opposed to a formula type approach, which is the same idea. What we talked about with the thing. So let's get an example. I think it really makes it make sense here. Okay, we got a table here that's got some information in it. I'm going to share these slides with you. So, positive drug test results. This is in no way. I heard a rumor Friday that we were going to drug test kids and all that stuff. It was a rumor started by students, spread by students. None of us had ever heard that already. So that may happen, but I don't think. I mean, it wouldn't be because I know anything about it. But anyways, just happened to be drug testing this. So don't think too much into this. We're just talking about drug testing. All right, positive drug test. 44 true positives, and then 6 negatives, false negatives. These are people that we knew were drug users before we tested them. Okay,
How do you know?
I'm not sure.
They
Maybe they declared it. Yeah, I use it. People lie. It's more likely that they lie than the result. Good, but we're assuming that people are honest. It was an anonymous.
They saw it.
They may have given us. They may have talked to their business associates. All right. And then the second row there is subjects that we know do not use drugs. There were 90 false positives and 860 true negatives. Okay, a false positive happens, when you know you're not on drugs and your drug test comes back saying you weren't. Okay, that happens. Okay, false positives happen. False negatives happen. We had 6 of the 50 that used drugs that came back as a false negative, but we knew I guess we watched them. Anyway, that's our data. This is our information. We're going to build everything on it. Okay. All right, so we're going to find the probability that the subject uses drugs and the subject tests positive for those drugs. Okay, we're going to find the probability that the subject uses drugs and that are given that the subject tests positive. Okay, so we take the probability that the subject uses drugs and tests positive. So look at our numbers here. That would be this group right here. Those are the ones we know are an and. They use drugs and they tested positive. So that's 44 out of, if you total all these up, it's 1,000.
What drug they test?
We're not sure. Could have been Tylenol. We're not sure. Doesn't matter.
Some drug.
Well, I mean, it shows up in your system if you take it. So, I mean, no matter what you take, it shows up.
Cyanide.
That would show up in your report. But and then on bottom, we're going to take the subject test positive. So that's the total number of positive results. So we had 44 that were true test positive, and then 90 false positives, people that we knew weren't taking drugs or didn't take the drug we were testing for. Okay, so that's 134 together out of the 1,000 people that were tested. Divide those two fractions, the denominators cancel out, and get 44 over 134, which obviously reduces. We get that 3 significant digit there. So the probability of a subject uses drug, given that they tested positive, is 32.8%. From our data here. Okay. That's the probability of B given A. If we randomly selected them. Okay. So we're finding the probability subject actually uses drugs, given that they have a positive test. So you think about drug testing and how, you won't catch people. Well, somebody that uses drugs from all the people that are positive testers, it's only a 32% chance that they actually do use drugs. That makes you kind of think about that a little bit more because of the statistics. But that's with that particular type of test. There are different types of tests that they can do for drug testing. So, this is where you kind of can get the arguments about, testing for welfare benefits, Social Security benefits, if you do drug testing for that. Well, what if it's false positive? I lose what I should be getting because of a false positive. That can happen. So you've got to, that's where that kind of falls apart, in my opinion. So those things happen. Nothing is absolute. All right. To incorrect the confusion of the inverse. This is what the title of the slide is. Confusion of the inverse. That's a hard thing. To incorrectly believe that A given B, that probability, and B given A are the same, or to incorrectly use one value for the other, is often called the confusion of the inverse. Okay? I don't know exactly why we need to know that. It's got that name. Use the one you meant to use. Okay? Don't, A given B and B given A are not the same. All of them. Sometimes they are, but not all of them. Okay? So be careful of that. Make sure we're getting those pieces there. You're going to get tables in your work here with things you're going to do. We're going to look at page 164. This section should be quick and easy. You'll probably finish it in just a few minutes. This section is a little more difficult because you got the given stuff. Okay, so 164, 5 through 32 for section 4.4. 4.5 is page 172. We're just doing 5 through 35 out of that. So this one's a little tougher. This one's not so bad. It should be pretty quick out of that. So my suggestion is work today. You got